Molweni, sanibonani, sishafile kunjani? I go by the name of Motizo. Welcome back to YouTube channel Yamanyora. Please hit the subscribe button, the bell notification, and love and like this video. Today, we're three kinds of pressures, and then we'll deal with two questions. So this kind of pressure, these three types of pressures is absolute pressure, the gauge pressure, and the atmospheric pressure. So the absolute pressure is the sum of the gauge pressure and the atmospheric pressure. So the atmospheric pressure at sea level is equal to 101,325 pascals, right? So the gauge pressure is equal to the density of the fluid, the gravitational acceleration, and the h. This h is called the pressure head. So we'll deal with this pressure head, especially when we're doing Bernoulli and the pressure losses in the pipeline. So now, I've drawn a picture of how these pressures differ, right? So we got the absolute zero pressure, which is where our datum line is. So remember, the absolute pressure is the sum of gauge pressure and atmospheric pressure. This is where we find the perfect vacuum, the absolute zero pressure. So on top of the atmospheric pressure is the positive gauge pressure here. And then here below the atmospheric pressure is the negative gauge pressure or the positive vacuum pressure. So the terminology might change, right? So remember, pressure changes with height. So in a different altitude, you'll find a different pressure. So remember, the atmospheric pressure at sea level is 101,325 pascals. So if we want to calculate pressure at a certain altitude or height, we got P at that certain altitude is equal to the atmospheric pressure, bracket 1 minus T. This T is the temperature change per meter, multiplied by that altitude, divided by TA. TA is the absolute temperature at sea level, right? And then raised to power G. G is the gravitational acceleration. R is the gas constant, which is 287 joules per kilometer Kelvin. You see this when you're doing more of a thermodynamics principle. And then the T is the temperature change per meter. So it's when you're calculating pressure at a certain altitude, right? So now when you go down, I've prepared just two questions so that we deal with this three kind of pressures, right? So we are told that the pipeline manometer indicates a negative pressure. Where is it? It's below the atmospheric, right? So it indicates a negative gauge pressure head of 50 millimeters of mercury. So we are asked to find the absolute pressure in the pipeline at sea level, right? So we know how much the pressure is at sea level. It's 101,325 pascal. So Pg is equal to rho, which is the density of mercury, 13,600, which is this one, multiplied by G, which is the gravitational acceleration, multiplied by the pressure head, which is 50 millimeters. So I just converted this millimeter to meters. So we get 6,670.8 pascals, which is our gauge pressure. So the question wants us to find the absolute pressure. So we know the absolute pressure is the gauge pressure plus the atmospheric pressure. So now we are told that it's a negative gauge pressure, hence why it's not a plus here, it's a minus, right? It is in this region. So it's below the atmospheric pressure. So now we subtract the gauge pressure from the atmospheric pressure, which we get 94.65 kilopascals. Right, let's move to the second question. The second question, we are told that the vessel contains 10.5 meters of oil of specific gravity 0.8. Remember when we were doing in the first lesson, we talked about the relative gravity or the specific gravity and all those sorts of things. I'll put the link for the second video on the description so that you go through them. So we are told that the specific gravity is equal to 0.8. So what do you do to this specific gravity to find the density of this oil? We multiply it by the density of water at 4 degrees Celsius, which is 1,000 kilograms per meter cubed, right? So now, and we are told the vessel contains 10.5 meters of oil of specific gravity 0.8 on top of 20 meters of water. Calculate the gauge pressure and then the absolute pressure at the bottom, which is very important. At the bottom, when the atmospheric pressure is 95 kilopascals, right? So why is water below oil? It's because water has a higher density than oil. So the oil will float on top of water. So this is why it's depicted in this way rather than water on top of oil. Right? So now we know how much the atmospheric pressure is. We are told that it's 95 kilopascals. The gauge pressure, we need to find the gauge pressure so that we find the absolute pressure. So now we have two kind of fluids. Remember, the gauge pressure is rho GH. So it's the density of that fluid multiplied by gravitational acceleration multiplied by the pressure head. So in the context of oil, we have 800, which we multiply 1,000, which is water at 4 degrees Celsius, by 0.8. We get to find the density of that oil. It's 800 kg per meter cubed. 800 multiplied by the gravitational acceleration multiplied by the pressure head, which is 10.5, plus the density of water. Remember, we are asked to find the gauge pressure and the absolute pressure at the bottom here. So now, for us to find the gauge pressure, we need to add the pressure due to oil and then the pressure due to water. So now we add them together and then we find them to be equal to 2.007 megapascals, right? So now this is our gauge pressure, how much our gauge pressure is. We are also asked to find how much is our absolute pressure. We are given how much is the atmospheric pressure. And we know that the absolute pressure is equal to the gauge pressure, which is this one, plus the atmospheric pressure. So we add them together to get 2.012 megapascals. I go by the name of Motizo. I'm out. Thank you very much.